Okay, so hello everybody. Welcome to the second lecture in our course on open systems, and we will pick up right from the place we ended before. That is, we were talking about time ordering and time-dependent Hamiltonians that generate evolution operators U that are given by time-ordered exponentials, right? And we make this observation, let's say, that this evolution operator is defined by this series, okay, where you have this time-ordered integrals, which we like manipulated a little bit last time. But this is often like convention is to rewrite it as a exponential that's attacked with time ordering operation. Okay, and we kind of talked about how it can be used, how it's defined, and some tips and tricks how to use it. And we will continue on with this discussion, reveal more tricks. But before we reveal more tricks with time ordering, I want to do one of the calculations we skipped last time, but it will be useful. So I will now jump to, before we continue with time ordering as an operation. First, let me do with you assignment 6, which I will quickly flash it to you on the PDF. So assignment 6. So this is quite simple. Show that when you take the evolution operator, you take a dagger of it, you reverse the time arguments, beginning with the end. Okay, and yeah. So let's do the calculation. Let me pull up my, there will be some useful tricks here. All right, so show that UTS dagger equals UST. Okay, solution. Again, every assignment, when you go to the PDF, which you can find on the website, you click the solution, brings you to the end of the document where there is exhaustive explanation, okay, for you to consume and to make fun of, or to compare with your own calculations. So you can always go back there and see some detail that maybe you missed here. Okay, but all right, so let's start by just taking the dagger of our operator, which is, again, we just use our good old reliable series formula, T duk, right? This is when in doubt, write down the series and go from there. This is my advice. And dagger. Okay, so what will happen here? Well, the simplest thing will be that dagger is also complex conjugate, right? So the imaginary, let me take this, imaginary unit will change sign. Okay, so we will get additional -1 to the power k for each term. Second thing, H or Hamiltonian is a Hermitian operator. So each H, when it's crucified with the dagger, it won't feel it. However, products of operators, even Hermitian operators, will be affected by dagger. And what happens, you just reverse the order, right? Which is kind of important for us because we are like the ordering of operators is like the thing we are doing here. So when I do the dagger, we'll get -1 to the power k, and u1 we'll get time ordering in reverse essentially. Okay, but for operators right now at least. So still the sum, right? Because taking a dagger is linear. -1 to k from the complex conjugate. The integrals, they don't care, right? These are just integrals. So we are still operating on the our standard time ordering, but H operators, they get reversed. UK, right? So there is something has changed. So now we want to transform it back to something that is again time ordered exp. Okay, so there is some work before us. Namely, we have to do something with integrals. We have to match up, reorder those integrals so that they match up with the order of operators, right? Then we will basically back to the beginning. But to do that, we have to do some tricks. And this is the trick that I will show, the identity I will show you now is basically the workhorse of many, or maybe even all algebraic manipulations you can do on this time-ordered series. And this identity, key identity, identity. So it's like, let's write it like this. So we have an ordered integral, ui duj, okay? And what will happen if I want to like pull the uj before ui, okay? How to do this? And the identity tells me, yeah, okay, you could do that. Ts duj, and the price to pay is that you do something like this. Okay, how to see it? To see it, you just have to write down unordered integrals. And there are at least two ways to like rewrite this into ordered form. One form is what we did on previous lecture with theta functions. So good old standard dui ui s duj plus st duj suj du I. Okay, that's one way to rewrite it. But there is another way to do it. SUI. We'll try not to make a fool out of myself. Oh no, sorry. I already made fool out of myself. Another way to rewrite unordered integrals. Okay. And this is simply you take this and split the second integral into 2 bits. TUI, TUJ plus TSUI, TUJ. Okay, agree? And they are equal, of course, because this is the same thing. And you see this guy this term we will cancel with this term, okay? And we are left with this and this, which is what gives us the identity, okay? So that's the trick. And in practice, it allows us to basically pull the integral from the back to the front, okay? Which we now execute. So we take our ordered integral as we are given them in our formula, and we start by taking the last guy and pull it to front, okay, going step by step. So to write down those steps, duk. So let me write it like this: u s u4 du3, okay, du1. So this is the last one we are pulling to the front, and du2 goes back, and according to our u3. Oh. According to this pattern, okay, you get something like this, right? So the thing of note is that now it depends, the lower limit depends on the variable we are pulling in front. And you go pull it through u3, u4, blah, 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 until we get to the very front, which produces for us u ps u1, and the rest of the guys we mangled along the way, uk, u1, u3, u2. So it's basically what reproduced here is again ordered integrals, but now the lower limit is bounded by the guy we pulled in front, right? And now we take u2 and pull it just before u1, and continue, iterate this procedure until everything is in order. So if we do the same thing for, I mean, almost the same thing, because we stop here with u2 t, and then we will be here t u2 du k, u2 u4 du3, and iterate, and finally we'll get st du1 u1 t du2 dots uk minus 1 t duk, right? Now we go back to our so we apply this to our series, k1 to infinity minus I k minus 1 k, and we have our rearranged integrals, uk minus 1 t duk, h u1 h uk. So this is almost what we need, right? Except it would be nice if the bounds were on top rather than below. So let's flip them, but flipping costs -1 sign. Oh, we have extra minus signs here to consume. Very nice. So we consume them and we arrive at the full formula. Okay, S T du1 T uk -1 uk and the Hamiltonians uk, which is time ordered except it goes from T to S. That's the only thing that's different. And this is what we were to show. All right. And it's all, again, this trick, okay, pulling the integral. If you know about this guy, or you know where to find it to remind yourself, you're basically almost everything can be done with that knowledge. Okay, so I hope that was fun for you. It was a little bit fun for me. And now we can, okay, so we got that out of the way, and now let's use T. Let's find some uses, useful things we can do with T as operation. So, as you saw, showing this, this simple dagger reverses stuff, it was kind of involved, right? You have to do some algebra, keep the indices in mind. There was some work to be done there, right? So now, when you treat T as an operation, right, that guy that rearranges products of operators in this manner that we described previously, some proofs can be skipped. Okay, instead of doing the algebra, sometimes you can just argue your way through out of doing the work. Okay, and I want to show you how you can do this kind of trick with T to show the composition rule. Okay, for those time order exps. Right, so composition rule. You can, of course, show composition rule in many other ways, for example, doing the algebra, of course, or through a Schrödinger equation, like we did on the previous lecture, but you can also attack it with using T. So with the composition rule, just to remind you all, you take T goes from W to T, okay? You compose it with U that goes from S to W, so they meet at the time W. And composition rules tells you that you can just stitch them together, okay? That's the composition rule. Okay, so how to do it without algebra? All right, so first thing to note, if you take exponent of two numbers, right? You know that this bad boy factorizes like this. You can say, okay, this is like composition rule, kinda, for numbers, right? But if you take exponent of two operators, okay, and you would like to, okay, let me like factorize it as well. But this is not so easy when A and B don't commute, okay? Why is that? How to see that it's not so easy? Well, you take left side, you expand it into series. There will be a bunch of factorials. Things get to the some combination of powers, stuff like that. You can expand the right-hand side. You will also have sums. You will have factorials, powers, and stuff like that. And all the factorials, all the powers will combine into what we would need to get this factorization. However, there's one very important distinction. On right-hand side, all the A's are to the left of all the B's, right? But on the left side, it's not like that. They are mixed up altogether, right? So unless A and B commute, you cannot like fix everything and recover the exponents. So there is no easy factorization because the ordering of operators matter, okay, with exponent. Bearing this in mind, let us get back to our task at hand. So we have u. It is an exponent, time-ordered exponent, hu du. Okay, and we want to do the factorization, essentially. We want to show the composition rule. So let's start by splitting the integral here into this integral into, one that goes from S to W and the other from W to T. So WT, HU du minus I SW H, maybe let's call this variable V, the V. We are still, in the exponent. This is all legal. Nothing suspicious happened. But we would like to. So this would be A, something that corresponds to A. This would be something corresponds to B, essentially. So we would like to split it in two. However, we know that this cannot be done for free because of the order. However, time order, we have T, the operation T, right? It acts on this whole stuff. And the rule of thumb about T is like, oh, when operators are under T, you can treat them like numbers because T will take care of the correct ordering afterwards, right? So let's just use this rule of thumb and let's just split those exponents while keeping them under T, okay? So we write it like this, E minus I WT U the U E to minus I S W V dV. It's all legal as long as we are still under one big time ordering. But now let's use some words. When you inspect those two guys, you see that U, the variable U, okay, will always be larger than the variable V, okay, because this integration goes from W to T, and this integration goes from S to W, right? So those guys, every operator that's under this X will be later than any operator under this X, okay? So in other words, the time ordering won't have to mix them up, right? All it has to do is to work independently on these operators and independently on these guys because they are always, guys from here are always in front, will always be in front of guys from here, right? So if this sounds like a convincing argument, then we can say, okay, so if that is the case, so let me write it like this. Du. If T will treat them independently, then I can just split it. Okay. But this is composition rule. Right? Yay! We've proven the composition rule by using power of talking a lot. Okay, so that was fun. We didn't have to do the all the algebra. We will do algebra anyway in a second, just to show you what would you have to do to get this result. But here is a word of caution. It sure was nice to, you didn't have to calculate, you just, argue your way through to get this result. But this is the dangerous part, okay? Because if you replace procedural algebra with talking, there is this risk, you run into risk that you will just convince yourself that you're making correct arguments, even though you're just, you are wrong. And it's not always so clear without doing the actual algebra to see if your arguments are really true or maybe you are mistaken. And the best case scenario is if you make your arguments and you just obtain a obviously incorrect result. Then it's like, okay, I see. There is something wrong in my way of thinking. But the worst case scenario, this is the real catastrophe, when you obtain the correct result anyway. And then you have no way to, you just think, okay, so my arguments were okay. I do the right thing because I got the right thing. But of course you can get true from false. That's possible. But now you are just oblivious to the fact, and okay, so now I use my trick to other things, and let's just prove more stuff. And it's like, this is just asking for trouble. So my advice is then to, it's tempting to skip the grind, don't do algebra, use some arguments, but you know what, maybe don't skip the grind. Okay, it's much safer to actually do the algebra, do the work. And if you are used to a couple of tricks that you have to use, it's not that bad. And anyway, once you prove all the all the identities you need, you don't have to go inside. You just use your time ordered X, and it's not like you have to calculate everything all the time. It's just you just prove a couple of things and live your life. So it's sometimes it's very tempting, sometimes it's very useful, but you have to be careful with using T as an operation. But the safest fallback is to write it down as a series and do the serious algebra on it, and make sure that everything works. Okay, so that was the word of caution. And before we go to the break, let's show the composition rule by doing the algebra, actually. Okay, so we jump into the assignment number, where is it? 7. It's AS7. Using only algebraic methods, prove the cont rule. Okay. Okay, so maybe I will be a little bit sloppy here with a lot of stuff to write. Yeah, no, it's okay. It's okay. We'll survive. It's all good. Sorry if it's too technical, but it's kind of important to really gain this mastery, to not be afraid of time ordering, because it will really be, we'll be using this all the time. It's like you cannot skip it. You have to be comfortable with it to the point that you start to manipulate it to your own ends, as we will do. Okay, so this is kind of important to demystify this guy. All right, so let's start with writing down the composition, and to just expand it into series. Expand both terms into series. So we will have from n to infinity minus in goes from w to t du n wu to du1 Hamiltonian hat times the other guy, 1 plus m from 1 to infinity minus im, but integrals go from s to w, du, not u, v m s v2 dv1 and Hamiltonians vm h v1. Okay. And now we have to do some rearranging. So the idea is to collect everything under one sum, essentially, which we can achieve by changing the names of variables, essentially, but keeping the track of the indices. Okay, which one is front, which one is in the back. And the way I wrote it here, I hope it will be kind of self-explanatory. So there will be floating term, let's call it w t d tau k. So I'm changing the names of variables to tau, both u and v. W tau 2 t tau 1. So this guy, what is this guy? This is basically when any guy from here hits identity here, okay? So this is the simplest guy, because you don't have to worry about all the hellish mixing with timings. So the other term we'll have to keep track which comes from the left guy, which comes from the right guy. But it's not so bad. It's not so bad. Just chill out. So this one, sum goes j from 1 to k. That's what I found out. It's kind of okay. Tau k. So here you probably recognize, because the integrals goes from w up, so those guys come from the left u. But we want to keep everything in one string of one sequence of indices. So let's enumerate it like this. And then we will have integral goes from s to w. So this is what comes from the right guy. And we just have to enumerate taus accordingly. S tau 2, d tau 1. So these are integrals. Sums, I can close the parentheses, and there are operators, of course. Minus ik, because there are always k terms. And we have, because we kept track of the indices, the product of operators is just simple, like this, okay? Just from k to to T1. But the integrals are all messed up. So this is the product. But on the other hand, we have the target, I mean, what we want to obtain. That is this guy, which again is 1 plus sum k from 1 to infinity minus ik integrals s to t tau. Let's keep the name of the variable 1, and we have our okay. So look, it's not that bad. We have a the imaginary unit with the correct power. We have operators are in the same order here and here. Just integrals. We just have to show that this beast here is actually the same as beast here. Okay. So this is our problem to solve. Just have to show that this is the same as this. How do you achieve this? Well, again, there is some iterative procedure that you can deploy here, and it's just simply you write down this guy s to tau 1, and you start bisecting integrals step by step. What I mean by bisecting, I just write it like tw plus w s d tau k s k1 no sorry tau k minus 1 s tau 2 tau 1, and we won't do all the steps, okay? I will leave some stuff for you, but you do the first bisection and you get what do you get? No. Shit. You can use this guy as tau. Well, that looks nice because this is the part of the integrals that go from S to W. That's good. The other guy may be a little bit more complicated because it looks like alien body here. And then we take this second guy and we split this integral into WT S. No, S. Oh. Okay. Right. W. Tau k minus 1. Tau 2 S. Tau 1. Okay. And again, split and repeat. So I won't write everything down, but once you do a couple of iterations of this kind of procedure, you will arrive at the conclusion that indeed this guy here is the same as this guy here. Okay, this I will leave for your own inspection, and this is all you need to show. So it's kind of not so hard. And at this now we can take a 5 minutes break. 5 minutes break. It's okay. No, 5 minutes. Okay, let's carry on. So now we go to the next step, the so-called disentanglement theorem. Don't confuse it with quantum entanglement. This is unrelated completely. This is just thing that people talk about in the 50s, maybe 60s. That's why they didn't, that was a good name for at that time. Now it's maybe not the best, but okay. So the issue is that here is the issue. Imagine that you have a Hamiltonian. Okay, so we have our generator, but there is a reason. We have some motivation for splitting it into two parts, the H0 part and V. Sometimes, and this is often motivation that comes up. Often it's like this is like V is a perturbation, let's say, small in some sense, but it's not necessarily the only motivation. But often this is how it comes up. And let us assume that the problem with H0 only is something we can solve. That is, operator U T. Let's write it like this, because this is a time-independent operator, so we can just use our non-time ordered exp, standard exp. So this is known. Okay, in the sense that we know how to calculate it, whatever. Maybe we have some analytical formulas. This is like the thing that's not mysterious. The whole Hamiltonian, well, that's a problem right now, but H0 is okay. This is under control. And now the idea is to we take the full evolution operator, so the one that has both H0 and V, and we want to, this is so-called pass to the interaction picture, or to disentangle H0 part from V. That's what disentangle theorem. In concrete terms, this means that we want to factor out the zero part from the rest. The rest I will use the same notation as before. And the question is, okay, what is this? What is this? Okay, what is this U? The reminder. Okay, the evolution operator in the interaction picture, sometimes it's called. And to make long story short, the answer is that this UT is given in terms of interaction picture. Interaction picture, which means that we have to define for ourselves the VT, V in the interaction picture, as this is sometimes called, which is a modified, this is the modified V operator from our original Hamiltonian. And the modification is you take U0, T dagger, V0. Okay, you sandwich V in the known part of the evolution, which transforms when you do the dagger, right? There's no time ordering, you just flip the sign of V. Okay, so we have V in the interaction picture, and the U, once we have this U T0, so the reminder, the evolution operator in the interaction picture is actually given by time-ordered exp. 0T V U du. Okay, where time ordering, of course, orders V operators, VU operators. That is, k from 1 to infinity, minus I k, our favorite integrals, uk, 0 u2, du1, and v uk, v u1. All right. And how to show this? Of course, there is assignment for that, but we'll do assignment here. So they are assignments, but they are kind of extra bits to calculate sometimes. It's not only as a homework. So let's do assignment 8. So the disentanglement theorem is this formula, okay, for UT, because you have the full guy, you disentangle the known part, the zero part. So the theorem is what is the form of what's left, okay? That's this is a theorem. Maybe it's overblown to call it theorem, but this is traditionally, I think this is how it's called. And assignment 8 is to prove the disentanglement, the disentanglement theorem, and in a special way by transforming the dynamical equation. Dynamical equation is just to remind you, a Schrodinger equation, but for evolution operator, right? Not for state, but for evolution operator. So to distinguish them, I will call this dynamical equation. So it's transform equation to interaction picture. Of course, you can prove it by algebra, right? You can prove it in a couple of ways, but this one is just to showcase the simple proof. There won't be too much writing here. So the dynamical equation I'm talking about here is the equation for the whole guy. So the derivative of this equals the full Hamiltonian, right? If I'm not using the U symbol, this is what the dynamical equation is, right? And the idea is to transform it into interaction picture, which basically amounts to substitute for this exponent this form, okay? So we can start by left-hand side. So we have dt. Do I use explicit? Okay. Minus ith0. So this is the zero part and the unknown part, u. So we just substituted the interaction picture of evolution operator, and this guy is unknown, right? But we can do something with the derivative, because this guy we control. So when I hit with derivative into the first bit, I just get my generator ut, right? Plus derivative hits the other term, the other factor, du t0 over dt. Okay, so this is the left-hand side. On the right-hand side, nothing much happens. Just rearrange the terms a little bit. Minus ith0, ut0, minus iv eit H0 ut. Okay, so nothing interesting happens here, but now the trick, maybe you saw this kind of trick previously somewhere on one of the quantum mechanics courses. You multiply both sides from the left with u0 to minus t, which essentially the inverse of the known part, and from left multiply from left. I don't know how to denote it. So multiply from left, from left. I don't know how to symbolize this, and equate the left hand side with right hand side. So maybe I should just write it like this: left hand side equals EITH0 right hand side. Okay. And what does it mean? What do we get in return? So for one, so this is left hand side. I multiply it with e to ITH0 from left. So this comes here, but H0 commutes with itself, right? So I can just move it, commute it through H0, then it meets this guy and they annihilate, right? You get identity here. And here they just eat each other for free. Okay. So you get here minus I H0 UT0 plus du T0 dt. And on the right hand side, again, commutes through H0, eats with this guy, but here it's not getting eaten. So we'll get IH0 UT0 minus I EITH0 V minus H0 UT0. Okay, so this guy cancels with this guy. Nice, very good. And this guy, what is this guy? This is the interaction picture of V, right? And so we arrive at the new dynamical equation that looks like any other dynamical equation with this generator, which is time-dependent generator. And we know how to solve those guys. We know the solution. T equals time ordered E minus I 0T V U du, which is the disentanglement theorem. So we got that out of the way. So that was disentanglement theorem for time-independent Hamiltonian. But of course, we can do time-dependent Hamiltonian. Time-dep Hamiltonian. Time-dep Ham. H of t equals H0 of t plus V also of t. Everything depends on time, the most general case. And this time, U0 t this would have to be time ordered exp, right? Let me modify our notation a bit. Let me add index here, h0. Just to remind us that time ordering is supposed to reorder h0 operators. Okay. It will be clear in a second why am I introducing stuff like that. Now the interaction picture. So again, we have VT, interaction picture of V, which is defined in an analogous way as previously, dagger VT. But V now depends on time also, right? UT0, 0. We can use dagger to flip the limits of the evolution operator. So this is our interaction picture of V in this case, and that's the evolution operator in interaction picture. So U without 0 is again time ordered exp minus I integral VU du. But this time I will insist on putting in this index to remind us that this time ordering orders V's, VTs, okay? Now, why am I so insistent? What's going on here? Let me explain. Why specialize T? Okay, what's the deal with that? So let's imagine that I'm sloppy. I don't specify what operators T is allowed to reorder, and just treat them as universal ordering. Whatever product of operators it encounters, it just reorders them so that the latest one is the in front, the earliest one is on the back. So let's see what kind of things we will be dealing then with. So let's take our guy, our VU du. So this is a universal T. It reorders everything. And let's just focus on first term of the series expansion. VU du, and there are more terms, but let's not look at them right now. It's not necessary. And now, all right. So well, one is not touched. Nothing has to be. We don't have to do anything with this. Here we have T, and okay, but V has some inner parts, right? VU has some inner parts. There is U. Too many U's. Dagger VU U0. No, what maybe not U. What other letter? Tau. Because it just looks so silly. D tau. Okay, that's other terms. All right, so I don't know. Time ordering tells me to order stuff, but when I look at this, sorry. Change the name, so this also tau. Okay. So this guy has time tau, all right? But all the operators in use, remember, this is time ordered exponents. So we have integrals, go from 0 to tau. So all the operators inside this guy are earlier than tau, right? And same with this guy. So I guess our time ordering should just take V and pull it in front. Okay, so let's do this. 0t d tau v tau u tau 0 dagger u tau 0 0, but this is 1. Okay. And similar thing will happen to all the higher orders. So when all is said and done, we will end up with exponent minus 0t v tau d tau. So not interaction picture. In other words, if this was the case, if this was true, so we would then show that time ordered minus I 0t h0 tau plus v tau is simply TEI 0t h0 tau t tau times minus I. Which is not true. This is wrong. We show this, but this is wrong. It shouldn't be like that. That is a mistake. And what was the mistake? Well, the mistake was using non-specialized T. It just confused us. We got inside interaction pictures of V, and we started to fiddle around with these innards. And that was a mistake. Okay, that's why we need this guy here to avoid this kind of confusion. Because if we use this notation, then we know, okay, this T is allowed to reorder V's, but as a whole, as an atomic expression, okay? Don't go inside, just stay on the surface, right? This guy tells us that we can that you just UK U2 D1 Z UK U1, and that's it. Order V as a whole because my index tells me so. All right. That's why I'm insisting on using this guy here. All right. So be aware of this thing. Don't forget it. If it's clear from context what is the operator you should order, sometimes you can skip this index. Okay, like and usually what is so you can treat this kind of formula as a maybe this kind of formula rather as a shorthand. Okay, so this means I'm ordering the thing that's under the integral, okay, as a whole. I'm not splitting it into parts and trying to figure out what to do with ordering there. No. This is like, okay, treat it as a whole. So to avoid any confusion, it's better to just add the subscript to T and be safe, okay? So that was the important lesson. And now let's specialize. I've done this. Okay, now the assignment for you. Okay, now assignment for you. So let me change to PDF. So we went through this, We were here. We just showed this was the spiel. Okay, so assignment for you, consider assignment 9, okay, which is to prove disentanglement theorem for time-dependent Hamiltonians. So what we are talking about right now, but using only algebraic methods. So no shortcuts with Schrodinger equation. Okay, do the work. It's a lot of fun. I promise. I promise. And of course, take a look, pick at the solution. If you don't want to, don't calculate everything, but try to like internalize the algebra I do there in the solution, just to see what's what. And then when you need to do it, you will know where to find it in the future. Okay. So 9 is for you. Okay. But 10 we can quickly do here, because we were doing the so above I showed you how you do the disentanglement when the time goes from 0 to t, all right? But let's say you have but let's say you have this kind of guy. So the integral starts from S, right? And I want to disentangle also operator that starts from S. Okay, is there something fishy about that? And there is something fishy, because if I disentangle this guy, my interaction picture here modifies a little bit, because I have you have two indices from S to U, which is not the same as VU, just U. Okay, VUS is interaction picture, but using the U0 that goes from initial S to the argument U, right? But you can still insist to disentangle from this U0 that goes from 0 to t in your reference time. And this is where you recover your our original VU. But there is a price to this, because another guy appears on the right. Okay. So maybe let's not prove this. Check out, if you are interested how to obtain it, check out assignment 10 as well. But just remember this, okay? This is word of caution, that sometimes take care that sometimes something can appear also on the other side of your disentangling. Okay, but I will point out when this will come up. But okay, you know what? Yes.
Explain once again what is wrong about what is. How is it different from normal disentanglement?
Okay.
The S is the zero.
Okay. So anyway, let's do this. So yeah. No. Okay. I feel I see I'm not making this clear. It's okay. It's okay. I see I'm messing up here. So assignment 10. So we have our Hamiltonian, full Hamiltonian. It has H0 t plus v t. All right. This is what we have. We have our full evolution operator. But let's make it go from S to t. H u t u. All right. And now we would like to disentangle from this th0. Dzień dobry. st h0 u tu. okay? And we would have the interaction, we will be left with interaction picture. So we would have TV, right? Because we need V in the interaction picture. E minus I, same kind of integral. And what we would, based on what I told you before, you would say, okay, so just write here U, VU, du, right? Where this guy, VU, equals U0 from 0 to U, VU, U0, okay? Where this is U0 from T to S. Okay, based on what I said before, this is what you would probably try to do, but this would be wrong. What actually would happen here, you have to modify a bit your interaction picture, because you are disentangling evolution operator that starts from S to T. Okay, so the price you pay for this disentanglement is that your interaction picture involves those evolution operators inside. Okay, so you would have to write here SU US VUS. Okay, all right, you see that? But you can still push forward and keep to your zero reference frame, the initial reference frame. You can transform it further. You can disentangle it even more. Disentangle more. And you can push it further. Let's write it like this: VT minus IST VU du, where this guy it goes from 0 to U. Right? But as it turns out, this is not for free, because there will be another guy that appears on the right-hand side of your interaction picture evolution operator. Okay.
The problem with the starting that this entanglement can be just taken from anything. This equation was not for general entanglement, but like entanglement starting from like S. Then we change it into the one that works from the start.
Yes. So we started at the very beginning by setting S to 0, so initial time to 0, and to define every interaction picture with 0 as your reference time, right? But if your actual full evolution operator starts from some other time, non-zero time, then it's maybe it's kind of obvious, but your disentanglement will like involve this information about the initial time. But nevertheless, you can still pull everything to your reference time, the one that we prefer, which is 0. But the price you pay for that is that there will be another guy on the right-hand side. Maybe it's there are use cases for that. Maybe when we will encounter them, I will point it out. But I feel I'm confusing you a bit here, which is probably true. But that was the problem in this assignment. Okay. So this is another tidbit to know. So we're running out of time a bit. There is some. I'm on the crossroads now, okay? Because we could carry on with maybe a more down-to-earth stuff, or you could allow me to indulge my. I mean, I would like to indulge myself here with some abstract spin-off, and I don't know if this is a good idea to talk about this, or you know what? Let me do it. Let me do it. This will come in handy in like a couple of weeks, okay? But and maybe you will find it kind of fun. It's a mathy thing about mathematical stuff, but it's very fascinating for me, okay? And I want to share because for now, this time ordering came up because we have Schrödinger equation, Hamiltonian depending on time. It's really time ordering. It's ordering time, right? But it's actually more abstract than that. And I want to like show this abstraction and actually to talk about those unitary operators in more abstract way, because there is a lot of very nice abstract math over it. Okay, the use case for doing time evolution is just one use case. Okay, but there is more to that. So I have this assignment 11. I recently added to the list, and I will talk about it for a bit, if we can. Okay. Wrong thing. So assignment 11, and it's kind of weird. The assignment itself it says construct an interpolation Interpolation, what I mean by interpolation is that you have an interval goes from 0 to 1, and you have a parameter, time-like parameter, and you have a function. Let's call it gamma. It's an operator value function, unitary operator value function actually. It's basically time ordered exponent. Maybe let's take plus here. We don't need minus. There is some generator here, u du, and there is gamma 0. It starts with gamma 0. And it is an interpolation. This gamma is an interpolation between, oh, we almost run out of time. Two unitary operators. Sorry, let me move this. So gamma is supposed to interpolate between gamma 0 equals I some h0, some Hermitian operator h0, and gamma 1, which is some e to I h1. So you know what linear interpolation between two vectors would look like, between two colors would look like. You know LERP, right? It's So this is like an interpolation, but for unitary operators. What the hell is going on here? And it's supposed to be like a time order. So what's going on? Well, and here is the math story behind this whole stuff. So unitary transformations, which evolution operators are unitary transformations, right? They change your vectors into bases, into new bases, whatever. They are formally elements of a SU group, special unitary group. Okay? It's called, you have SUD, where D is the dimension of our Hilbert space. Okay, for qubits, that would be D would be 2, for example. And SUD, this group of abstract group of unitary transformations, is classified as so-called Lie group. This is a SUD is also a Lie group. You don't have to. This is like super extra stuff, extra bits. Lie group, okay, Lie group means that one, it is a group, but it is also a differentiable manifold. Okay, differentiable manifold. It means that this is a space. I know it's kind of hardcore, but this is a space that locally it maps to Euclidean space. So locally, it looks just like, standard vectors, whatever. In practice, what this means, because that was some jargon, you don't care about this, nobody cares about that. But in practice, this means that any unitary operator can be parameterized with a coordinate on a properly big hypersphere. So what I mean by that is like, if I take any operator, like let's say I, so one of those endpoints, our interpolation, you can parameterize it as E to I sum L goes from 1 to D square minus 1, TL times V, say IL, where phi I is a vector, it says coordinate. And so I'm sorry, this is kind of stupid, but it's also kind of beautiful. So this is a coordinates, but coordinates on the sphere. Okay, dimension is D square minus 1. So you have dimension higher than higher than 2, then it's difficult to picture it, but it's a sphere. Okay, for dimension 1, that would be a circle, so it would be coordinate on the circle. Okay, and these are generators of the group. Okay, so this is also a vector of Hermitian operators. D square minus 1, which you can always choose as a orthogonal basis. Orthogonal basis in the sense that you get TL scalar products. Okay, I'm going overboard here. Sorry for that. One more thing, and I will stop. Okay. Scalar product, which you can choose as a standard trace product, and you can always pick this set of generators so that they are orthogonal to each other, even normalized. So, for example, if you have qubits, so D equals 2, those generators I'm talking about here, that would be sigma, poly-sigma matrices, X, Y, and Z. And this is also how it maps to the Euclidean space. Okay, because you know that you can treat those guys as like a axis in coordinate system, right? So you have your any unitary operator is like so it's like a point on the hypersphere, right? So for qubit point on the sphere, I guess.
One dimension are rotation.
Yeah, like no, there's more group stuff here, but there's no. There is overlap. There is overlap there. For qubits, that would be true. All unitary operators are rotations, but for higher dimensions, there is a subset that is rotations, but there are like higher order stuff that's not. There is room for more kind of like things. But it's a for qubit it's actually 1-to-1. And the last thing I would say here before because we run out of time, right? So using this parametrization, this shows that you have your if I sketch my SUD as this hypersphere, right? So you have your here would be like a pole. So this guy would be some point on this hypersphere, okay? Right. And now if you have a point, it's only a small step to imagine whole paths on the hypersphere. Path is just a collection of points with some chronological order. Okay. So for example, if you take so we could construct a path, simple path where this guy is an endpoint. You know, if you define your path ui tau, which would be simply I tau hi, okay, tau goes from 0 to 1, then this is a path in the sense that it starts at the pole, at identity, and then it goes along the meridian. I think this is called meridian. From geography, latitude, longitude. So we have this nierównoleżnik, tylko ten drugi, południk, whatever. So you go along this meridian, and you go. It's like the straight line on the sphere because your this generator, this vector here, it points in one direction all the time, right? So you just go from one to you just go straight to the end. Now you can have a path that swivels around, right? But to do that, you would have to this guy here would have to change in time along the path, right? So this is why this is the most general form of a path on our SUD. If your Hamiltonian is just you can because generators are bases, you can decompose any Hamiltonian in this basis, and the coefficients are the coefficients of this decomposition in the basis are actually those phi coordinates. So that's why you can use sigma matrices to like write every Hamiltonian as a combination of sigmas, which then generates your rotations or unitaries. Higher dimensions is just more sigmas, let's say. And if you have time-dependent coordinates or time-dependent Hamiltonian, which then implies that you have coordinates that are dependent on time, you would have some path that goes maybe even to the same endpoint, but along some weird meandering stuff. So our unitary evolution operators are paths on the hypersphere of SUD. And if you have, this interpolation I'm asking in the assignment to find is basically, okay, find the path that connects 2 points. Like you have it goes from the pole to H1, H0, and you want to close it with some forward triangle, basically. And what is the generator? What is the time-dependent coordinate here, phi, that would give you this path that will connect those two guys? I don't know. It's kind of fun to me, but I hope it was fun for you as well. So this is like some math stuff. And believe it or not, there will be some point later down the line where this will come up. Okay, this like abstract view of unitaries. It will come up. So thanks for your attention, and see you next week.